So who here has seen important separators or important cuts in action? Okay, who here has heard of the term important separator or important cuts? Okay, brilliant. Um, so I am to understand that you all know iterative compression, right? So I'm going to assume that you all know iterative compression at this point, which we won't require until later in this lecture. But when we get there and you have forgotten something, or you feel that there's something you didn't really quite understand the last time, just let me know. So what exactly is the plan for this lecture? Well, I'll define this pretty cool tool called important cuts. And then we'll look at some very useful combinatorial properties of this tool. And then we'll look at some applications. Some applications will be very obvious. In particular, one will be very obvious. You look at the problem and you'll see, so this is a problem where this tool seems applicable, and then we'll see that in fact the application is also quite easy. But in reality, this tool ends up being applied not on the main problem itself as you would expect, but you start with your problem, you throw in a lot of your standard techniques, branching, iterative compression, whatever. And at some point, once you've learned enough about the problem that you're handling and you have uncovered enough structure in the input that you're working with, then you try to add more tools, and one amongst these would be important cuts. And typically, this is applicable when, in the course of solving your problem, you uncover some pairs of vertices or sets of vertices. So, right now, I'm going to talk in very, very vague terms. I'll formalize everything. But at some points in your, while solving the problem, you end up coming up with maybe two sets x, y, and say that my solution, let's say it's a vertex set that you're deleting to achieve a certain property, amongst other things, happens to also be an XY separator, right? In which case, this tool could be something you think about. Now, since I mentioned this, can anyone think of a problem where such a phenomenon does occur? So as you're solving it, you throw in some basic techniques, and then suddenly you have to like separate x and y, or equivalently hit all paths from x to y in some graph. OCT. So OCT was one such problem where if I just give you the problem and the input, it's not clear what you're separating from what. All you know is that you're cutting some things in this case happens to be odd cycles. But then once you uncover enough structure in the instance, you point out two sets x and y and say, from this point onwards, it is sufficient for me to solve the problem by finding an xy min cut, whatever. Right, so this is one of the hidden scenarios I talked about. And we will see one such specific instance where we will uncover some things that you need to separate, but you will no longer be able to just use a min cut. At which point we'll have to start talking about something called important cuts. Okay, any questions at all? Excellent. So let me just write down some definitions so we are all very clear when we make certain assertions or write some lemmas, etc. And one other comment that I need to make is until I specify otherwise, we will be working on undirected graphs. And at some point we will switch to directed graphs, but I'll point that out. So here are a few definitions that we really need to be clear about. So let's say x, y subset of G, S. So an edge set S is an XY cut if there is no x to y path in G minus S. Right, so G is a graph, and if you want to be formal, you say in G. So you just remove these edges from the graph, and in the process you end up hitting all paths between x and y. And since this is an undirected graph, xy paths are yx paths, so the ordering doesn't really matter, so you don't have to worry about that. Secondly, I don't want to keep writing English all the time, so let me define some more notation. Let me just define it here itself. I'm going to define this set. So this set is the set of all vertices that are reachable from X after you delete S. It's fairly intuitive notation, right? So this is nothing but all those. So I can rewrite this as this reachability set is disjoint from Y. That's basically what's being said here. Right? So far so good. Okay. Again, a couple of standard notation. When I say standard, you will find this in different fonts in different books. So let me just define this anyway. Let's say for all x of Vg, delta of x denotes the edges going out of x. Right? So if I have x here and delta of x is precisely those edges which have exactly one endpoint in x. So this would be all those let's see, E equals I don't know, a comma b, such that x intersection a comma b 2 equals 1. And let's denote by dou of x the cardinality of this set. Right, so I suppose these are all notations you've seen in some form or another, right? So you would have just seen different alphabets being used for this, but for this lecture, this is the notation we would go with. Okay, so now that you know what a or an xy cut is, let's define the star of the show, if you will, important cuts. An xy cut S is important if it is minimal. Well, I have not defined what minimal means, but minimal in this case means inclusion-wise minimal, right? So S is a minimal xy cut if no strict subset of S is also an xy cut. Yeah? And you have two very crucial properties, and there exists no xy cut S prime such that the size of S prime, well, S prime is no larger than S. And secondly, what you can reach from X after you remove S prime is a strict subset of what you can reach from X if you remove S. Right, so as of now, it is just a definition. But what am I saying here? Well, here is, let's say here's X, here's Y, and let's say this is S and this is R of X comma S. I'm dropping the subscript if the graph is clear or it's not important, etc. And if you have any confusion at all, just stop me. Right? So S is an XY cut. when do we say it is actually important? It's important if there is no other cut which is somehow more important, and by that what I mean is you should not have, right, some other cut S prime. Let's say S prime also contains these edges and maybe some other edge. So S prime is the green one, and this is right. So you have another XY cut S prime, which is intuitively closer to Y, or in this case farther from X, such that it is no larger. Now, how have we formalized this word farther? This is how we formalize that. Right? So there should not exist an S prime which is at most, which has size at most that of S, and allows X to reach strictly a subset of what it was, strictly a superset of whatever it was reaching before. So questions about the definition. So clearly, important XY cuts form a subset of all XY cuts. Yes. Could you say? Yes. So it should not be larger than S. No, it doesn't. Right. So it shares these edges. It no longer has this one, but instead it has the green one. Right. So XY cuts clearly are a subset of, well, important XY cuts are a subset of all XY cuts by definition, and it's not difficult to see that they are actually a strict subset, right? Because here is an example. You can complete this example by adding some other edges to see that here is a set S which is an XY cut but which is not an important XY cut. So important XY cuts are a strict subset, right? So if you look at the space of all XY cuts, your important XY cuts sit inside somewhere strictly. But now this brings up the question, well, how many of these are there? Well, that seems like a very vague question at the moment. Let me now make it a bit more formal and a bit easier. How many important XY cuts of size 10 are there in the graph, right? So any thoughts on how many XY cuts of size K there can be in the graph? Well, 2 to the n is, well, 2 to the m is an upper bound for sure. Anything better? Or at least a lower bound? Can it depend only on K? So what is my question? Number of XY cuts of size, or give me an upper or lower bound. So we have loose upper bound. Can you give me some lower bound? Could this be true for some function f? Any thoughts? Guesses? Yeah, so I'm only focusing on XY cuts of size at most K, and my question is the number of such cuts bounded by some big function of K? Basically, could it be independent of n, the size of the graph? Any thoughts? Sorry? If you have a click. Oh, okay. But so then what is my x and y here? Because I'm talking about xy cuts of size at most k. Okay. But okay, could you describe the example again? Fine. In one cycle. Okay. Fine. Fine. Okay. Fine.
Now any two from first, from one side and the right from left hand side and right hand side, any two edges will form a cut in that.
From between what and what?
Top and
Ah, okay. So this is your x, and this is your y. Okay, good.
so there are so many combinations.
Yes. So here is a counterexample that you can't have the number of these cuts independent of n. Right. So let's look at a slightly simpler example. So let me take a path. Right. So this s t, and this is my x, and this is my y, and I ask you, well, this is a path, and I said k equals 1, and I ask you how many xy cuts of size 1 are there. Right? So if this were true, then that would have to be a constant, but clearly it depends on the size of the graph, because you can make this path as long as you want. Right? So this is not true. However, we will be able to prove that the number of important xy cuts of size at most k is indeed bounded by some function of k. Now, why is this useful? Before we go there, so quite often in problems you will be able to prove that the solution contains or intersects an important xy cut at most k for some x, some y in some graph. Right? So what you could do at that point is, if you were able to compute this big set, it's big but it's not too big, it's still a function of k, then you could just branch on all the separators that you have inside this set, because each of them has size at most k, and there is only f of k, many of them. So that's typically the way you would end up using it. Right. Don't worry, we will see a concrete example. So if this went completely, ignore it. There's not a problem at all. So now we essentially want to build up towards proving the statement. But before we go ahead, any questions? Okay, then I have one. Could I erase this? Excellent. So, a quick question, a puzzle pretty much. So if I said k equals 1, this tells me that the number of important xy cuts of size at most 1 is some constant. Any guesses on what this constant is? Okay, we have 1. Any other answers? Okay, why is it 1? You're right, it is 1, but okay, I'll let you think about this. We'll prove the full statement, at which point you will see why it's actually 1 for k equals 1. But in the meantime, I'll let you have some fun thinking about this specific question. Okay. Well, there's actually one other piece that I need before we go ahead and prove this. How many of you don't know what submodular functions are? Excellent. So I'll define what submodular functions are, and we'll see one function that you're all quite familiar with is actually something that I keep calling submodular. And I will leave the proof of that as an exercise, but I'll give an intuitive explanation of why that is true. Well, first of all, definition. So let's say I have a set system U, and I'm a function over subsets of U to real numbers. We will just work with natural numbers. Is submodular if uh, so the only constraint is for every pair of subsets of U that you take, the function satisfies this inequality. So who has heard of diminishing returns, the phrase diminishing returns? Okay, so submodular functions are actually functions that give you what are called diminishing returns. Since most of you have not heard it, let's completely ignore it. But if you are interested in some extra reading, I would recommend looking up pretty much any reasonable textbook which mentions the relationship between submodular functions and diminishing returns. So now, why are we talking about this? When you're dealing with cuts in graph, this is actually very crucial because the cut function in graphs is submodular. So if you remember, I defined dou of x equals. So this is just to make sure we talk about a specific graph. So now this is a function. So in this case, my u is my entire vertex set. Dou is now a function mapping vertex sets to natural numbers, which is defined in this particular way. And as it turns out, this pretty natural and well studied function is submodular. So it satisfies this inequality. And this I'm going to leave as a proof. But what exactly, so how would you prove something like that? How would you prove that this is submodular? Well, I'm going to take a couple of these sets and I'm going to prove to you that this inequality holds, right? So let's say you have A, you have B, and now you look at the edges. So what sort of edges are there? Well, you have edges that go from, I don't need more than one, so I'm just going to draw one. So there are edges that go from A minus B to V minus A union B, and symmetrically from B. Then you have edges that go from A to B, but which lie completely inside B. There are edges which look like this, and there are edges which look like this. Now, what are the edges that contribute anything to these numbers? So when I say these numbers, now picture dou of A, dou of B, dou of A union B, and intersection B. Right, so all you now really need to do is go through each type of these edges. This is type 1, type 2, type 3, type 4, type 5. And what you really need to do is check the contribution of each type to each of these terms. For instance, let's say this is type 1. So type 1 edges contribute to this and to this, but not to this or to this. Right, so it's just very simple case analysis. You need to sit down, stare at it for 10 minutes, and this is really it. So it's pretty straightforward, which is why I'm skipping the proof unless there are any questions. So the takeaway is really that the cut function satisfies this inequality. Right? Can I erase the definition of submodularity? Yes. Because I'm not going to erase it completely, I'm just going to rewrite it in terms of the cut function. So you won't lose the inequality. Well, this is no longer a definition now. This is a claim, and the proof is exercise. Now, what is one very, very frequent use of this fact? This is something you'll see whether you're doing FPT algorithms, approximation algorithms. In fact, more so when you do approximation algorithms, you will see this property being utilized over and over and over. Let me give you a small window into how this is done, at least one way in which this is done. So let's look at XY min cuts. What is a min cut? Well, an XY cut of minimum size, right? Now, let me look at two XY min cuts, and S1, S, or let me write it like this, SA, SB are minimum XY cuts. Now let me look at these sets, X comma SA and right, so these are both vertex sets, right? So this one is defined as the set of vertices you can reach from X after you remove S sub A, right? So these are both vertex sets by definition. So this I'm going to define as my A, this I'm going to define as my B, and notice that dou of A is precisely the size of the set and dou of B is precisely the size. So far so good? Okay, so now let's look at A and B. So I know that the edges going out of A form an XY cut. So what that means is X has to be somewhere here, Y has to be somewhere here, because del of A and delta B are both XY cuts. Is this picture fine? Right, so for now I've just taken two specific A and B which cross. I've just taken this particular example for a reason. But the claim that I'm making is X is contained in A intersection B and Y is disjoint from A union B. Questions about this? So now notice that A intersection and are both XY cuts. Right, because X is contained inside each of these sets, Y is disjoint from each of these sets, and delta says I take all edges leaving that set. Right, these are both XY cuts. Now can we infer something interesting about the sizes of these two sets? So let's try to plug in the submodularity inequality, which tells us that this is true. Now, notice that this guy has like some minimum size. I'm going to denote it with lambda. This is also minimum. So it has to be the same size, some lambda. Now, since these two are both xy cuts, each of these numbers must be at least lambda. You can't go below the min cut number. But then what does that mean? Very good. So these are all actually lambda. So what this means is you take these two crossing min cuts, A and B. So what you could do is start with this and you can create two uncrossing min cuts or non-crossing min cuts, because these two are now in inclusion relation, right? So one is contained inside the other. And this is what is called uncrossing. So this is something you will see very, very frequently in approximation algorithms, where you have two cuts, and it's often useful for your proof if these reachability sets that you work with are laminar. And by laminar, I mean no two of them cross. So for every pair of them, one is contained inside the other, right? So it is useful to get such sets. So what one would do is start with A and B and say, hey, look, these are ugly for my proof. Let me replace them with two other cuts which are both min cuts. So instead I could now work with these. Right? So we will also see why this is useful for us, but the uncrossing technique is very, very common in approximation algorithms. Any questions? Right, so if you take nothing else away from this lecture, this is a really, really cool piece of a technique to remember. Okay, so after that digression, let's get back to our main goal, which is proving that for all k. Can I erase this? I'll leave the inequality here. Well, you could uncross them to get two cuts for sure, regardless of the size. But what this inequality gives you, what it gives you is an upper bound on the sum of their sizes. Now, I don't know whether that's useful for you, like in other situations, but this is one common way of using it. In fact, today you will see two situations, one where they are minimum and one where one isn't. So we might end up answering your question today. If not, just let me know at the end. Any other questions? Okay, so let me write down some nice properties of these cuts, which will be useful for us. So let me write down. Okay, so there exists a unique maximal set, which I call R max, such that y and is xy cut. So what this says is, well, if I look at minimum xy cuts, that's what this says, and I start looking at their reachability regions, and I look at their inclusion-wise ordering, there is a unique maximal one. So why is this true? I'll at least let the statement sink in. This denotes the size of the minimum cut, by the way. I don't think I defined it formally, but yes, very good. So can we go ahead to the proof? I'm not going to write down the proof formally because we just saw it, but is the statement fine, first of all? Right? So for the proof, suppose that this is not the case, right? So then you have two such sets. So this is R max 1, and this and delta of this set is a min cut, min xy cut, and here is R max 2, which also has the same property. Here is x, here is y. And what we just proved is that delta of R max 1 union R max 2 is also a minimum xy cut. Right, so if these two are both minimum, the number of edges going out of the intersection and the union separately are both also equal to the size of the min cut, which makes the union and the intersection also min cuts, or at least the reachability region of min cuts. But do you see that now this R max 1 union R max 2 contradicts our choice of R max 1 and R max 2 as maximal sets. Okay. So since this was a proof sketch, I'll just erase this unless there are any objections. Great. Now, what is a very natural consequence of this lemma? Well, yes. And so, if I look at all xy cuts of minimum size, so there's some of them, there's at least one, I look at some of them, and now I look at the important ones amongst those by just applying this definition. I'll just apply this definition and filter out guys that are not important. What this says is that I'll just be left with one. So just to be clear. So the first question is, why does this follow from this? It is actually just a corollary. Just need to be sure that we all see it. So take your time, stare at it, and let me know if you have any questions.
Is it necessary that maximal set is important?
How are you defining the maximal set first? Because here the maximality is defined by looking at all those sets, all min cuts. From among those, I chose maximal one. Okay, so now can you describe your?
I'm just asking, like, no, you among all the min cuts, you have one maximum min cut. It's
The one with maximal reachability region.
yeah,
Yes,
maximum min cut.
exactly.
That is unique.
Yes.
So I'm asking, is that unique thing an important set?
Yes. Well, good question. Yes. The answer is yes, and that really is understanding that is the proof for why this follows from this. Right. So let's try to actually prove this using this statement. Yeah, just to be sure that we understand this. Again, suppose not. Which means that there are at least two important xy min cuts, right? So there exists S1, S2. These are both important and they are xy min cuts. Their reachability regions. So here is reachability x comma S1 and this one is reachability x comma S2. Let me know if you want to if you want me to write bigger or something. Right, so x is here. Thanks, and avoid it. So, do you want me to rewrite any of this? Oh, okay, fine. Right, so here is reachability x comma S1, x comma S2, and here's my x, here's my y. Now, since they are both important, what does that mean? It means that if I take, let me just focus on one of them for now. This is x comma S1, this is x. What does this say? If I take any other minimum xy cut, well, this property is not violated because they are both minimum, right? So S1 is minimum. Let me take some S1 prime. This can't be violated, which means this must be violated, right? Which means, let me just zoom back a little bit. And in my effort to answer your question, I have tied myself in a few knots. So could you remind me your question?
No, I was just asking whether the maximum set that we found there,
Yes.
whether that is the unique important XYZ.
This one.
Yeah.
Yeah, that is true. Yes, that is true. So let me think. Now we're just trying to give some very enlightening proof. But anyway, so let's try to just prove it as it is. So suppose that this is not the case, then you have S1 and S2 which both look like this. And then what did we do here? We said, hey, look, let's look at the union of these two sets. This is also equal to lambda x comma y, which, yes, exactly. Which means that now the delta of this set is now a minimum xy cut that contradicts the choice of S1 and or S2 as an important cut according to this definition. So I'll pause for a while here and let you ask questions. Right, so here is S1, and I claimed that, hey, S1 is important. But then you come to me and say, but look at the edges going on this, that is also a min cut. And then you tell me, hey, but you claimed that S1 was important, which meant that this cut cannot be minimum because it clearly reaches more, but that is a contradiction. Okay, so can I erase this? So I'm just going to leave the lemma statements because that's what we will rely on. To Okay, now let me write. Yes.
Can't we just prove that the reachability of x comma s is maximum for the targets? Because that has the maximum number.
No, you're right. That's what I wanted to do, which is why this is just a corollary of that. You're right. But because I was getting lost, so I just went back to the original one. But now complete your thought. I think.
No, I'm just telling you, if you take the vertices that are reachable from S, that is
Yes.
exactly the A union B that we
But this requires another proof, right? So it is true. It's completely true. It follows from things that we've seen, but I have not stated that, so I did not want to use that. But you're completely correct, right? As far as understanding goes, you have understood it correctly. Anything else? Okay, so let me stare at important separators a bit more, important cuts a bit more, and now let's make sure that we understand a bit more about their structures. We already have some interesting properties. Now, let me ask you the following. I take an important XY cut, let's call it S. Now, let me take an edge inside this cut S and I delete it from the graph. Now, do you think that the rest of S, which still remains, is it an important separator? Is it an important XY cut in the new graph? So, let me just write this. So, let S be an important XY cut. It's no longer minimum, it's just an important XY cut. Now, my question is S minus E an important XY cut in G minus E for E and S? So I just deleted from edge from the separator. So now it's a new graph. What about the rest? Is this true? Is this clear? Right? You removed an edge and you did not suddenly create a path from X to Y that is disjoint from S minus E. Very good. But what about importance? Could we have lost that by deleting an edge in S? Fine. Well, you can forget about unique maximality now because that applied only for minimum cuts. We are no longer talking about minimum cuts, so we need to be careful. But go on. That is fine.
all the cuts of smaller size, no cut of smaller size is great, more reachability from calculation.
Okay, that's the right idea. Okay, good. Any other thoughts? So your answer is yes to this question, really. Yeah. Okay. Does anyone who says no?
If I take a important separator for G minus E
Yes.
and add E to it, so it will get
Yes. Yes, so that's really the proof. So the answer is yes. So again, how's the proof? Well, suppose not. Which means that in G minus E, S minus E is not important. And when it is not important, you need another cut that witnesses this one's non-importance, right? So what you would do is, so let's say this is X, this is S, and this is Y. Now let's say this is E. So I've removed it from the graph. Now look at the reachability set of X in the graph G minus E. That's really the same, right? Okay, so now when you said, hey, S minus E is not an important separator, it's not an important XY cut in G minus E, which means according to the certificate cut S prime such that, so there exists, let me just write it with this one, so there exists an XY cut S prime in G minus E which violates this property, right? Such that because you just removed one, and G minus E, comma prime is a strict superset S minus E. Right, so for contradiction, when you assume that this guy is not important, it must be because of the existence of this S prime. But now, what you would do is, let's look at S prime union E. Right, so now I just add E to S prime, come back to my original graph. And what am I left with? Well, this we already agreed is the original reachability set. And the reachability set in G of X prime union E, well, it can't be any less than this. Right, so what you have now is a new separator S prime union E in G, which according to this definition violates our premise that S is an important XY cut in G. Right, so you delete E, you go to this subgraph and you use this definition to take this hypothetical violator separator, violator cut, and then you add E back to it, and when you come back to the original graph, that would be a violating cut for your original important cut. Questions? Okay, so that is one. So property, let me just, nah. Now let me write down another one. If so what am I saying here? Well, we know that S is an XY cut, but suppose that S also is an X prime Y cut for some much larger X prime. and we know that S is an important XY cut, then we can sort of transfer the importance also to X prime Y. Right, so what do I mean? Here there is again, well, here's X, and this is my S, Y, and let's say this is X prime. So not only is S an important XY cut, it's also an important X prime Y cut. Any thoughts on how one would prove this?
Same thing, you can assume this is not and there is an
Good.
important. Then you can say that is important for S also, it's a contradiction.
Very good. So the proof is very similar. So suppose not. Suppose S is no longer important for X prime. That must mean that there is a violator. Now, if you take that violator and look at that violator's reachability set, that must be a strict superset of this by definition, right? So that guy has to look like this. And the size of the corresponding cut is at most the size of S, which means now you have violated the importance of S as an XY cut. Because what you have is still an XY cut, because X prime contains X and it's an X prime Y cut.
If we S is a minimal X dash Y cut, then
Well, could you say that again? It's a minimal
X dash Y cut.
XY cut or X prime Y? Oh, okay, X prime Y cut. You're saying you need minimality there.
Because suppose the particular edge which was in the cut, is both of its endpoint are already in X prime.
But remember that it is an important XY cut, which means it has minimality built in there.
For X.
Sure.
Okay, X prime is superset, right?
Ah, okay, you're right. So what you're saying is, if you simply say X prime, X prime is a superset, that's not good. Yes, you're right. So, it's a very good point. Okay, let me now walk back and see if we all understood what the objection was. Right? So the way it's written, it simply says X prime is a superset of X. So now X prime does not need to be here. Maybe X prime is this S plus some neighbor of Y. Or not neighbor of Y, but something that is completely not reachable from Y. Right? I mean, it's a different connected component. Right? So then, I mean, what are we even saying? So in this case, this is trivially true. But then, no, wait. The way I have phrased this statement, it's still true. The statement is still true. Why would the statement be violated?
Let explain the X and an edge from the cut S.
Which one?
Some edge from the cut S.
Some edge. No, X prime has to be a vertex set.
No endpoints.
Both endpoints.
Yeah, that's what I meant.
Okay. Okay, that shouldn't be a problem. Okay, fine. So this is my X prime. Let me use a different color. Something like this.
Yes, so
That's whatever goes out of here.
yes, so S is now not minimal.
But S is also no longer an X prime Y cut already. So look at my new X prime.
Is still
It should still be an X prime Y cut. Does that make sense? So your example is not the issue, but let me here and let's say that there is another set here. Let's say this is Q, and Q has neighbors. Well, actually, never mind. I think I'm trying to find a counterexample which doesn't even exist. So let's just take a step back and ask ourselves, do we all agree here? So one of the examples that I mentioned, what if there were some disjoint connected components and I take stuff from there into X prime? Well, S would still be an important X prime Y cut, right? So that is not violated. So these two properties are very crucial for our bound, right? So when we prove our bound. So any other questions? Okay. So now I need to erase something. Can I erase this inequality? I think we've stared at it long enough, and if you want me to remind you at any point, just let me know. All right. Oh, brilliant. Lemma 4. So let's try and continue gathering more and more interesting properties of important cuts, assuming we are all on the same page so far. Okay. Now, let so you remember R max, it's the same R max. So this is my claim. Okay, any thoughts on why this might be true? That is the essence. So we are again going to use the submodularity, really. That's what we are going to do. Essentially, so again, wow.
Why do we need to use submodularity? Can't we just use this definition? Because we know that R max is exactly this XY important XY min cut.
Good.
And you know that that is an important, this important, like what, RG of X comma S, that must be a super set of this RG of S comma.
But why can't I have? That's a good question. So, what would happen if I had, let's say this is my R max. So X is here, Y is here. Now my new cut is going to look like this. Well, so R max is this one, right? So this is reachability of X comma S for some other XY important XY cut S, where the size of S is strictly greater than lambda. Right? So the number of edges going out of R max is the minimum number. This is some huge number. So why can't this exist? Yes, that would be how the proof goes, but let's just make sure that you see that simply based on the definition alone, nothing precludes the existence of such an example. Right? So that is the first thing that we really need to understand. This could happen, nothing stops us, but as was pointed out, suppose this does happen. Let's just throw in some modularity. Yes. So if you take, so you know this is anyway the min cut, and you know that the number of edges going out of the intersection should be at least the min cut. So if you just plug in these numbers here, what you would end up with is dou of, you take the union this number is at most S. Right, so just take those four terms in the inequality, plug in the fact that this is lambda, this has size S, that's what goes out. The size of the set going out of the intersection must be at least lambda. What you're left with will be this, right? So because of submodularity, this situation cannot occur. So what this means is if you look at any important separator, no matter what size, and you look at its reachability set, that must go beyond R max, which is the reachability set of that unique minimum importance separator. So nothing inside can ever be part of the part of this important separator S. Okay. So there's just one more lemma, and then we are ready to prove what I've been promising you all this time. I think I've just figured out a way to quickly break all of these. So I can't say that they were all broken beforehand. So okay, so there's just one other lemma that we need, and it's not going to be a difficult one. What we are basically going to do is just put together stuff that we've learned so far, and make some cleaner conclusions, which we can then implement directly in the proof of the number of important separator bound. Right, so so let be an. So notice that now I've switched from writing like S subset of edges to this. So R is the reachability region, and the corresponding cut that I'm talking about is delta of R. It's just a small switch in notation which makes it easier for me to write this specific lemma. Is this fine? Right, so okay, so then I'm going to claim that the following things hold is an important R max to Y cut. Why is this true? Very good. So it should follow from, well, lemma 4 says that the reachability set of S also includes R max. And lemma 3(2) says that if I set X prime equals R max, then important cut, which means it is an R max Y important cut. Right? So this would be L4 plus L32. Okay. So what do I want to say next? If E is contained in whatever goes out of R max, and I'm going to switch. Okay. Let's hope third time's the charm. And in my cut. So I'm just picking an edge which is in both my important XY cut and the cut corresponding to R max. Then what, S minus, or rather there's no S, minus E is an important XY cut in G minus E. Good, very good. So this is already written here, right? But the statement is still true. Yes? So let me just write it. But you agree that if I add this also, the statement is true, simply because of lemma 3, 1. Right? I'll explain. You'll see later why I wrote it in that way, because I just want to invoke it as a black box. And also to test if people are awake. Very good. Well done. So now I need one more. Um, if here's an edge, PQ is an edge that is in the set of edges going out of R max, but that's a bad place to break. Minus the R, where, well, one of P or Q should be inside R max. Right? That is why it goes outside. So let's say P in R max. Then is an important R max union Q, comma Y cut. So what am I saying here? Well, if I look at R max, and here is an edge PQ. Now I promise you that PQ is not in delta R. So it's not part of this important cut I'm talking about. Then I claim that delta R is actually an important cut between this set and Y. So not only is it something, it's an XY cut, it's also between this and Y. So Y.
The R max is contained here and you just add PQH to do.
Yes, so here we have that R max is already contained in the reachability set. And this premise allows you to also infer that Q is also contained in the reachability set. Right? And then you just plug in lemma 3, 2. So this is really all the pieces that we need. These are really all the pieces we need, and now we'll go ahead to the proof of the bound. I think this should be a good time if you have any questions. Could I erase the definition of important cuts? Because I'll need some place to write down the proof of the bound. Well, it is of course super critical, which is why I'm really waiting for a strong yes, but there isn't one forthcoming.
You can just keep the two conditions and erase the top part, because that's what you need to refer to.
True. That is true. So, is that what is? Does this seem like a reasonable compromise? So, or you could try and convince IMSC to buy some good smart boards. So I could just move stuff around. But anyway, let me see if I can.
You could actually erase the top two lines at least. That's just English. Like that does not exist extra.
Fair enough. And since there were no protests, it's too late for complaints. All right. So, what is number of important XY cuts of size at most k in G. Let me denote this by alpha x, y, g, k. Right, so that's what it denotes, and this is at most 2 to the 2k minus. So that is the claim. So let's be sure that we understand everything in the statement. Any questions? So basically, we want to prove that this is my f of k, the one that I promised you at the beginning. But we will prove it by proving this, which is actually easier to work with. Okay, and so the proof will be actually by induction on that number, this 2k minus lambda. So we're going to induct on that. So induction on. Now, as we go along, you will notice that the proof that I'm describing is constructive, which means you can turn it into an algorithm. Right? So at the end of the proof, we'll revisit it and make sure that we all understand what that means. But as we go along, try and see if you can spot why every step can actually be made algorithmic with everything that you've learned today. Okay, so what are my base cases? I actually need what if k is what if lambda is greater than k? So then there are no xy cuts of size at most k. So that's one base case. Well, what if k is at most 0? So then again, so either there are no cuts of size at most k or the empty set is the only one. Right, so these are the base cases. Now let's look at the induction step, and let's try to use lemma 5 to prove this. So let's try to do the following. So now you have induction k is greater than 0, lambda xy is less than k. So let's look at all cuts in alpha. I know alpha is a number, but I hope it's clear when I say all cuts in alpha g x, y, g, k, right? I'm going to use it as a set as well. Set of all important x, y cuts of size at most k in G. Let's look at one such cut, and let's compare it with R max. We already have a few interesting statements here. Well, we know that delta R is definitely an important R max y cut. That's just a fact. So let's try to do one thing. Let me try and compute, or let me take up R max. That's existential. Your task is to see why this is efficiently computable. X, this is y. So what this lemma, specifically this one, says is that any important cut is not going to take edges from inside here, because all of these guys are going to be reachable anyway. So really the question comes when you stare at edges going out of R max. Now let me pick an edge PQ that goes out of R max. Now let me look at an arbitrary important xy cut of size at most k. There are only two possibilities. Either this edge is in that important cut or it's not. Okay, so suppose it is in the important cut we are considering. Any idea what we can do? How can we count those important XY cuts that contain E. So that's what our counting process is going to be. We are going to split our counting into two. On one part, we are going to count all important XY cuts containing E, and we are going to count all important XY cuts that don't contain E. There's only two possibilities, and then we add them. So what about the ones containing E?
S minus G is an important expression.
Very good. So I'm going to count on the one hand alpha x y g minus e and k minus 1. That I'm going to count this. Now, suppose you are able to count this. How do I count important cuts that do not contain E?
Put X union Q.
Is it X union Q? That, what about R max?
R max.
Right? So if you're using lemma 5C, then you need to use R max union Q. Taking Q is also enough, but I'll let you worry about this later. But for now, let's just plug in the lemma as it is, and I'll count these as R max union Q, Y, G, K. Right? So we all agree that if I count these two quantities, then what I want is really the sum. And what I want is upper bounded by the sum of this as well. Ooh, 4 minutes. Okay. So now the next question is, why can I count these two? Can I use the induction hypothesis and claim that this measure 2k minus lambda has decreased in both cases, in which case I can then apply the induction hypothesis and that would work. So specifically, what do I want? To prove one, I want to say that twice k minus 1 minus lambda g minus e x comma y. So this is the measure here in that branch, if you will. I want to say that this is strictly less than 2k minus lambda g x comma y. And I want to prove that 2k minus lambda g R max union q comma y is strictly less than 2k minus.
The first case is K because the min cut size does not decrease.
Yes, very good. So in the first case, well, k has dropped by 1, which means 2k drops by 2. But on the other hand, lambda cannot drop by more than 1 because you only deleted 1. So this is true. Well, on the second hand, what about the second one? In this case, I claim that this lambda is at least 1 greater than this lambda. And the reason is, if that weren't true, then dou of this set, or rather lambda of this pair, would still be my original min cut, which would go on. Exactly, which would be of min cut and covering R max and Q, which cannot happen. Right? So of course this was a bit vague, but I hope you understand why an improvement is made in each branch. And what the induction hypothesis says is the number of, so this value is at most 2 to the 2k minus lambda g x comma y minus 1, and it's the same here. right? So you just plug in the induction hypothesis because in both these cases, uh, you're dealing with a strictly smaller measure, and then you take the sum of these two numbers because, as we already agreed, the splitting that we did was exhaustive. You pick an edge that goes out of R max that is either in my important cut or not. So it's exhaustive. Questions? So to sum up, what have we seen today? Well, we've looked at the definition of a new object called important cuts. We've seen that important cuts of bounded size are bounded in number. So in the next lecture, you will see why this is very, very useful when you try to prove fixed parameter tractability. And in fact, there are some recent works where people use this even when dealing with some problems in P. So typically in FPT, you're dealing with NP complete problems, right? So OCT, vertex cover, etc., etc. But there are some very nice results where you are now starting to work with problems in P where importance cuts, even though their number is exponential, like 4 to the k. But for certain applications, k is small enough that it's actually polynomial. K is log n, let's say. Right? What else have we seen? We've seen the uncrossing argument, which, independent of anything else that you see related to important cuts, that is a useful piece of knowledge to have. Right? At least the term uncrossing is something that's useful to remember. So in the next lecture, Saket should do what is called the edge multi-way cut problem and the feedback arc set problem on directed graphs. I think you've all seen the feedback vertex set problem already. On directed graphs, this was a very, very big open problem for many years until 2008, when the solution at that time was given using important cuts, and it was quite surprisingly elegant. And you will see that there are other problems for which people had given like very complex algorithms, which once you now start phrasing in terms of important cuts, now you start getting really elegant algorithms, not to mention that the previous ones weren't. My God, yes. There are no other questions. Thanks a lot for putting up with this.